Video, we're going to be practicing higher order derivatives. If you want to follow along, the links to the companion worksheet are in the description below, so let's get started. So the idea of higher order derivatives is we're not just finding one derivative, we're finding several derivatives in a row. So here for this first one, we want to find the second derivative for y equals 4 square root of x cubed. Now before we find the first derivative, what we're going to do is we're going to rewrite this in exponential form. So we're going to rewrite this as y equals 4. Now instead of x square root of x cubed, I'm going to rewrite that as x cubed to the 1/2 power. And now since we have two exponents, we can multiply them. So we have y equals 4x to the 3/2. And this will make things a little bit easier for us when we go to find the derivatives. So the first derivative is going to require power rule, and we write that as dy dx. So power rule says that the power comes down, so times 3/2 x to the 1/2. And we'll simplify this. 4 times 3/2 is 6x to the 1/2. Now to find the second derivative, what we do is we take the derivative of the first derivative. And the way we write that is we write d2y over dx squared, like that. A little awkward in the terminology, but this is how we write the second derivative when we have x and y. And so with power rule, again, we bring down the 1/2, and now it's x to the negative 1/2. And so to simplify that, we multiply 6 times 1/2, that's 3. And then in the denominator, we're going to have square root of x. And so there's our second derivative. So let's move on to number 2. Here we've got cosecant of x is our function, f of x, and so we want to find the second derivative of that. Okay, well we have done the derivative of cosecant before. If you want to look that up, that is in one of our previous videos that we did about trigonometry derivatives with quotient rule. And so the derivative is f prime of x. And so the derivative of cosecant is negative cosecant x times cotangent of x. Now that was a rule we already had, but to find the second derivative, this is going to require us to use product rule because we have two functions that are being multiplied. So first we'll find the derivative of cosecant again. So that's negative cosecant of x times cotangent of x. Now we still have cotangent that we didn't derive. And now we have the second term. Now keep in mind the fact that the negative distributes over everything. So the first term is negative and the second term is negative. So that means we are subtracting. So we subtract cosecant of x, we don't find the derivative of that, times cotangent of x. And the derivative of that, again, is on that video. We'll have a link to that below. That derivative is negative cosecant squared of x. So to simplify, we have two negatives, they'll cancel, and we have two cotangents. So cosecant of x times cotangent squared of x. We have a negative and a negative, so this has become a positive. And then we have cosecant, well, we have three of them, so cosecant cubed of x. Now what you can also do is you can simplify this a little bit further by taking out the one cosecant that they have in common. So we have cosecant of x times, and then what we're left with is cotangent squared x plus cosecant squared x, like that. Some teachers may be happy with leaving it in this form. Some teachers may want you to factor out the one term that they have in common. So I leave that up to you to decide which one you need. So for the next one, number 3, we want to find the second derivative of this expression, and this is going to require quotient rule. So our derivative, we have x as our variable, our independent variable, and s is our dependent variable. So this is ds dx. And so quotient rule says low d high x times 2x plus 2 minus high d low, so minus this expression times 1, so minus x squared plus 2x minus 1 times 1 all over low low, which is x squared. Now we will need to find the second derivative, which means we will have another quotient. So we'll need to simplify this. So in the top we have 2x squared plus 2x minus x squared minus 2x plus 1 all over x squared. And that simplifies to, well, the x squareds, they leave us with just x squared. The 2x's cancel out, plus 1 all over x squared. So now that this is as simple as we can write it, now we'll find the second derivative. So similar to number 1, we're going to write this as d2s over dx squared. And so using quotient rule for this, low d high x squared times 2x minus high d low x squared plus 1 times 2x all over low low x squared squared. So now we've simplified. X squared times 2x is 2x cubed. Remember that this negative distributes into everything. So we have negative 2x cubed minus 2x all over x to the 4th. The 2x cubes cancel out, so we have negative 2x over x to the 4th, and we can cancel one of the x's, and so that leaves us with a final answer of negative 2 all over x cubed. On to number 4. Now this one is uses implicit differentiation, but we can still find the second derivative. So first we find the first derivative implicitly. The first derivative is going to be 6x squared plus 2y times dy dx, and that's going to equal negative 4 dy dx. Now what we have to do is we have to solve for dy dx. So that means everything with dy dx needs to get on one side of the equation, and everything without dy dx goes on the other side of the equation. So I'll add the 4 dy dx over, and I'll subtract the 6x squared. So we have 2y dy dx plus 4 dy dx, and this equals negative 6x squared. Now we can factor out the dy dx, and we leave 2y plus 4 equals negative 6x squared. So dy dx, the first derivative, is going to equal negative 6x squared over 2y plus 4. Now, that's only the first derivative, so we're going to have to continue on to find the second derivative. And so to do that, we're going to have to use quotient rule again. So if I want to find the derivative of dy dx, that's our second derivative. That is d2y over dx squared, and that equals, now quotient rule, low d high, so 2y plus 4 times, so low d high, and d high is negative 12x minus high, negative 6x squared, d low, so the derivative is 2 dy dx all over low 2y plus 4 quantity squared. So we have the second derivative as we want it, but we're going to have to do some simplification here. So let's give myself some room. d2y over dx squared. So when we multiply this out, we get negative 24xy minus 48x. Here, the two negatives cancel, so it's plus 12x squared dy dx all over 2y plus 4 quantity squared. Now, more often than not, what will happen is that your teacher will want you to write this exclusively in terms of just x and y, and the teacher will not want it written in with a dy dx there. So what we'll need to do is we'll need to replace that with something in terms of dy dx. Well, this is what we found up here. We can use this formula and substitute it down here. So that's what we'll do. So negative 24xy minus 48x plus 12x squared, and we replace dy dx with negative 6x squared over 2y plus 4 all over 2y plus 4 squared. Now, at this point, we just have to simplify this fraction because it's a little awkward to have a fraction within a fraction. So what we do is we multiply the top and the bottom by 2y plus 4. Why? Because that will clear the denominator from this term right here. But what it will also do is it will add that factor onto the other two terms in the numerator. So negative 24xy times 2y plus 4 minus 48x times 2y plus 4 plus 12x squared all over, and on the bottom we'll have 2y plus 4, and this time this is cubed, because if we multiply it on the top, we also have to multiply it on the bottom. So let's simplify the top. So this is going to be negative 48x y squared minus 96xy minus 96xy minus, that will be 192x plus 12x squared all over 2y plus 4 cubed. And so these two terms are like terms, so we can combine them. Negative 48x y squared minus 192xy minus 192x plus 12x squared is our numerator, and our denominator is 2y plus 4 cubed. So this is our second derivative, exclusively in terms of just x and y. All right, so moving on to number 5 now. That one asks us to find the second derivative for sine squared of 7t. Now what we have here is we have three functions here. And what I'll do is I'll get rid of the 2 here and write it like this. So we're squaring the entire quantity. So this is the outermost function. Then inside of that we have sine, and then inside of that we have 7 being multiplied onto t. So to find f prime, we first have to look at the outermost function and say that we're squaring that. So the derivative of that would be 2 times whatever is still inside, which is sine of 7t. Now we have to look at the derivative of the inside, which is cosine, and we leave 7t alone. And then finally we look at the derivative of 7t, which is 7. So in all we have 14 sine of 7t times cosine of 7t. So that's our first derivative. Now to find our second derivative, we're going to have to employ some product rule. So f double prime, and that should not be x, that should be t, my mistake. Now 14 is our constant, our coefficient, and that will just hold on. So sine of 7t, that derivative is going to be 7 cosine of 7t. And then we leave cosine alone. And then plus 14 sine of 7t times, and then we find the derivative of cosine of 7t, and that is negative 7 sine of 7t. Okay. So 14 times 7, that should be 98. And then we have cosine squared of 7t. And then we have plus 98, or excuse me, minus 98 sine squared of 7t, like that. And so that is our second derivative for f prime. Now, if you remember your trig identities, we can factor out 98, and we're left with cosine squared of 7t minus sine squared of 7t, and this is all equal to just cosine of 14t. That is one of the double angle identities for cosine. So moving on down to number 6, here we want to find the third derivative. So here we have s as our independent, r is our dependent variable. So we do have a little bit of chain rule to deal with. So dr ds. So the outside function is sine, that derivative is cosine. The inside function is 2s, the derivative is 2. So we have cosine, and we leave the inside alone, 2s times 2. So our derivative is 2 cosine of 2s. So to find our derivative of this, we have d2r over ds squared. And so this derivative will be negative 2 sine of 2s times, the derivative of the inside is 2, so we have negative 4 sine of 2s. And then finally, our third derivative is going to be d3r over ds cubed. And so we take this, and it's going to be negative 4 cosine, that's the derivative of sine, of 2s times 2, and so our third derivative is negative 8 cosine of 2s. Fortunately, chain rule was rather easy because every time we took the derivative, an extra 2 came outside. All right. Now number 7 is a little bit trickier because it asks for the nth derivative of e to the 3x. So what we need to do is we need to establish a pattern with the first few to see, okay, what's the general rule? And then we'll write what that general rule is. So our first derivative is dy dx. And so e to anything, that derivative is itself, e to the 3x. But we also have to take the derivative of this inside function, 3x. So we multiply by 3. So we can write that as 3e to the 3x. So there's our first derivative. So our second derivative, d2y over dx squared. Now 3 is just a coefficient. That's going to hang on for the ride. And we've already established that the derivative of e to the 3x is 3e to the 3x. So we're just going to multiply by 3e to the 3x. So we have 9e to the 3x. And so to find the third derivative, d3y over dx cubed. So now we're going to have 3 times 9e to the 3x, or 27e to the 3x. Now, they all have e to the 3x in common, which is good. What's different about them is this, 3, 9, 27. But these are all powers of 3. And this is 3 to the first, this is 3 to the second, this is 3 to the third. And they match up. First derivative, second derivative, third derivative. So if I want the nth derivative, I'm going to write dny over dx to the nth. And so my coefficient out front is going to be 3 to the nth power times e to the 3x. That's my formula for the nth derivative. So I'm looking down at number 8. Here we want the fourth derivative of f of x, and what they give us is f double prime. So this is the second derivative. So that means we need to take the derivative 2 more times to go from the second to the fourth. So f triple prime of x, that's going to be, well, the derivative of 2x squared is 4x, and the plus 1, well, that disappears. And the fourth derivative, we tend to write this with little Roman numerals up above. Now, some books will write it with little numbers in parentheses, but it differs from book to book. And so using power rule, this is x to the first power, and so this will become 4x to the 0, or just 4. So that is the fourth derivative. The key to this problem is understanding that you don't start with f of x, that you start with f double prime. And since you start with f double prime, you only had to take 2 more derivatives. Now looking up here at number 9, we want to find the fifth derivative of g of x, but we're given that g prime is sine of 4x. So we only need to take 4 more derivatives in order to find the fifth derivative. So what is g double prime? Well, power rule says that the outside derivative is cosine of 4x times the inside derivative, which is 4. So 4 cosine of 4x is the second derivative. The third derivative, g triple prime of x. Now the 4 is a coefficient, so that just hangs on. The outside derivative is negative sine of 4x, but we also multiply by the derivative of the inside. So we have negative 16 sine of 4x. Now for our fourth derivative, we write Roman numeral 4. Our coefficient stays with it, negative 16, times the derivative of sine is cosine of 4x times 4. That's the derivative of the inside. So our fourth derivative is negative 64 cosine of 4x. And so finally, our fifth derivative, we bring down the coefficient, negative 64. The derivative of cosine is negative sine of 4x times 4. So our coefficient is positive 256 sine of 4x. That is our fifth derivative. Now notice that we took the derivative 4 times, and we went from sine to cosine to negative cosine back to positive sine. So our last question asks us, what's the smallest value of n for which the nth derivative is cosine itself? Now this idea is kind of similar to what we had up here in number 9. And that is, we started with sine, turned to cosine, then turned to negative sine, then to negative cosine, and then ended up back with positive sign. When we take trig derivatives with sine and cosine, when we keep on deriving them, they form a cycle. So if this is f of x, f prime of x is going to be negative sine of x. F double prime of x is going to be negative cosine of x. The third derivative is going to be positive sine of x. And then the fourth derivative is going to be cosine again. Now, if we wanted the fifth derivative, well, that's just going to follow the same pattern. This will be the 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. So there's a whole bunch of derivatives of cosine of x that will be itself, but we want the smallest value. And so the smallest value is 4. That's the smallest derivative where cosine's derivative is itself. If you liked the video, please give a thumbs up. For more videos like this, click the subscribe button. If you're a teacher, please share this with your students. If you're a student, share it with your classmates. If you got a suggestion or problems that you want to see worked out, type a comment below. To support the channel, click the Patreon link to help keep this going. Thanks so much for watching. And remember that the only way to understand something is to do it.